Hi there, and welcome to today's class. For today's class, we'll be studying the concept of work, energy, and power. And after studying these, we'll be looking at some past questions for both JAM and WIEC on this particular topic. All right, so for this topic, first things first, if you look at this topic here, there are three key words in this topic. The first one is work, the second one is energy, and of course, we have the third one as power. So I will take each of these one by one. I'll define them, list out their mathematical expressions, and of course, solve past questions on each of these. So first things first, let's look at the concept of the first one here, which is work. All right, let's start with work. Work is also called work done. So it depends. All right, so you can either say it's work or work done. Right. So saying work or work done is literally the same thing. Now, in science, when do we say work is being done in science? In science, by definition, in science, work is being done when a force moves a body through a distance in the direction of that force. All right. So that's how we define work done in science. So work is said to be done in science when a force moves a body through a distance in the direction of that force. Now, I want to point out some things from that definition. Three key areas in that definition. The first area is this. We said work is said to be done, number one, when a force. So the first thing that must happen for work to be done is that a force must be applied. So for work to be done, the first idea there is that, or the first condition there is that force must be applied. Number two, they said when a force moves a body, the second condition for work to be done is that that force must move a body. So I'm saying this, if I come here, I have this board here. If I stand on this board here and I keep pushing this board with all my energy for the next 5 hours, now so far as this board does not move, I've literally done no work, although I've spent time and energy in trying to push the board. So for work to be done in science, a distance must be covered. If no distance is covered, then no work has been done. And number three, we said the body must move in the direction of that force. Very important thing, okay? The direction is also important. So I'm saying, if I hold this piece of chalk here, right, and I'm to throw this piece of chalk to you. Now, if I throw this piece of chalk to you here, I expect that this piece of chalk should be going this way towards you, right? So if I throw this piece of chalk towards you like this, I expect that the chalk is going towards you. Now, what happens if I have a piece of chalk and I throw it towards you, and instead of the chalk to move towards you, it stops halfway and starts coming towards me? At that point, it's no longer physics work done, or it's no longer physics force. It becomes what there? Spiritual forces, right? All right, so I think that's like the concepts there, right? So three things there. Number one, a force must be applied. Number two, a distance must be covered. And number three, the direction should be in the direction of that force. All right, so with that explained, let's look at a mathematical expression for the concept of work done or work. All right, so having considered what work done is, let's look at a mathematical expression for work done. Now, mathematically, work done or work, okay, so let me use work done this time. Work done is equal to the product of force and distance. All right, so I'm saying mathematically work done, W, is equal to force F times distance. Let's call distance S. So this becomes the mathematical expression for work done, force times distance. Now, if you are to bring in SI units, we said that work done, W, is equal to force is measured in Newton, distance is measured in meters. So you can say that work done is measured in Newton meters or joules. All right. So joules is your second unit for work done, where the relationship between Newton meters and joules is that 1 joules, write joules as J, 1 joule is equal to 1 Newton meter. All right, so joules becomes the universally accepted SI unit for work done. An alternative SI unit for work done is Newton meter, as we clearly stated. And of course, joules and Newton meter are the same thing. All right. So 1 joule is equal to 1 Newton meter. So we have this. All right. So having considered this, let's look at something there. Let's look at the concept of. Okay. So with this, let me explain something with this. Now, recall that I told you earlier that I said that if you apply force, and it doesn't matter how long you're applying the force, if a distance is not covered, then no work is done. And someone will be like, but how true is that? Like, you're literally applying force to move something for so long, but that thing has not moved. So, but you're already sweating and you're already being stressed from that. So, how do we say that no work has been done? But here's a mathematical explanation for that. Look at this, please. So, we said work done is equal to, let's say I apply a force of, let's use a very high force, right? So let's use a very high force. Let's say 10 to the power 9 Newton. This is literally a giganewton, right? So I apply a force in moving, let's say this board here, and I'm applying a force of this value so big, but then this board is not moving. So if this board is not moving, the question is this: what distance has this board covered? For the fact that this board does not move, the distance covered is what there? 0. And of course, we know that anything times 0 is what there? 0. So in this case, we can see that work done is equal to this times 0 is 0. So this is why we say if a distance is not being covered, it doesn't matter the amount of force you're applying. So far as a distance is not being covered, the work done is what there? 0. That's it. So a distance must be covered for work to be done. All right, I think we've expressed that one there. Let's look at another concept of work, which has to do with expressing work in terms of a field. All right, let's look at expressing work in terms of a force field. Now, recall that we said a force field is simply a field where an object can experience a force, right, from a distance. That's what is called a force field. Now, when it comes to a force field, two things there. When a body is being lifted or dropped in a force field, the work done is equal to the mass of the object, times acceleration due to gravity, times the height to which the body is either lifted or falls. So I'm saying in a force field, and I've defined a force field as simply a region where a body experiences a force from a distance without a close contact. All right. An example of a force field is simply a gravitational field. So in gravitational field, if I throw this chalk up there, it comes down. I don't need to have gravity rising to pull it down. No, the chalk naturally comes down. Why? Because it's being attracted by what there? Gravitational force. All right. And the reason is because the force is actually in a gravitational field. That's the concept of a force field there. This force, this chalk here, is being dragged down by a force. What force? The force of gravity. And it's being dragged down from a distance. I didn't have gravity coming up to drag it down. No, gravity would naturally attract it so fast it's in a gravitational environment. So that's the concept of a force field. All right, so in a force field, here's what to note. When an object is lifted or it's dropped in a force field, note that the work done, W, is expressed as the product of the mass of the object, acceleration due to gravity, and the height to which the object is either picked up or dropped in a force field. Right? I'll take an example to buttress this point. So let's look at two quick examples to explain these two things, and then we move on. All right, so let's take a first example. The first example here says a boy of mass 50 kilogram runs up a set of steps of total height 3.0 meters. Find the work done against gravity. Now, in this case here, here's what to note. Please. So we're saying that if I'm to draw a diagram for this, we're saying that you have solution. You have certain steps. Let's say from here, you have this step here. Maybe the boy runs up a staircase. They said the total height of the staircase is about 3.0 meters. So from here to the bottom of the staircase, about 3.0 meters, I have this. Okay, so the boy runs up this. So let me use this to represent the boy. Okay, so the boy runs up from here, goes up the staircase here, such that the total height covered is three. The total height, that's from the bottom here to this point, is about 3.0 meters. And it said the mass of the boy is about 50 kilogram. So I'll take mass M as equal to 50 kilogram. Okay, we have to find the work done against gravity. Now, here's what to note, please. All right, so here's one thing to note. When we did the concept of free fall, for free fall, you had your free fall equations. And one of the key concepts in the free fall concept was that if a body is being moved against gravity, that if body is being moved upwards against gravity, we said the equation becomes minus g, right? But when it comes to work done, please, we don't consider that concept, all right? Because work done should not be negative, basically. Okay, so I'm saying this, when it comes to free fall, there we just say the work is done against friction. We don't say, okay, start putting negative here. No, leave it as positive. Instead, just say work is done against friction. All right, so in this case here, it's as simple as the work done, W, is equal to the mass of the boy times gravity times the height covered. In this case, that's equal to mass of the boy is about 50 kilogram times gravity. In this case, did they give us a value for gravity? Nope. They said we should use gravity as 9 points. So let's use gravity as 9.8. Of course, it's a constant, times the height covered by the boy is about 3.0 meters. So times 3.0, or just 3. All right, so I'll get my calculator and punch this very, very quickly. So what I have here is as simple as 50 times 9.8. So I have 50 times 9.8 times 3. If I multiply this, I have 1470. This is the work done. So my next task is to bring in my SI unit, which is joules. So I have this joules. So the work done in a field, right, in a force field, work done in a force field is equal to mass times gravity times height. That's literally all about this. All right, let's take a second question on this before we move to energy. So question two, let's look at this. Question 2 here says, okay, so before we look at question 2, let me point out something very important. Now, this case here was how we calculate the work done for a body moving upwards. What about in a force field? What about if I have for a falling body? Let's look at how we calculate the work done for a falling body. Something very critical. I want to show you two things there. First things first, let's say the body is falling directly under the influence of gravity, or let's say the body is falling perfectly vertically. So let's say I have this distance from here to here, and let's say the distance from here to here, let's call this h. We are calling this h, and now we are saying that a body starts from somewhere here. This body has a mass of m. For a case like this, where a body falls perfectly vertically in a force field, like a gravitational force field, we can say the work done, W, is equal to mass times gravity times height. That's for this. All right, so example 2. Example 2 says, a loaded sack of total mass 100 kilogram falls down from the floor of a lorry 2.0 meters high. Calculate the work done by gravity on the load. All right, so solution, let's get this done. So as usual, our first task is to list out given parameters. What's the first I'm given? That they said a loaded sack of total mass, so I'm giving the mass m as equal to 100 kilogram. That's my first task. They said falls down from the floor of a lorry. All right, the floor of the lorry is about 2.0 meters high. So they're giving you height number 2, height h as equal to 2.0 meters. You have to calculate the work done. So work done, W, is equal to unknown. Now, I want you to observe something in these two questions. For the first one, you have to find the work done against gravity. Now, this case, it's against gravity because the body is moving in the opposite direction of what? Gravity. That's it's going what there? Upwards. So when the body is going upwards, we said work is done against gravity. But in this case, now look at the question again. It says, find the work done by gravity on the load. Why do we say the work done is by gravity on the load? The answer is simple. It said the what? The loaded sack is falling. So if something is falling, literally it's going downwards. And if it's going downwards, it is going in the same direction as what there? Gravity. So we can say the work done is by gravity on the load. So see the difference there. When it's work done against gravity, it's going upwards. That's if the distance, if the body or the loaded sack or the mass or the body is going upwards, we said it's against gravity, work done against gravity. Meanwhile, if the body is coming downwards, we said the work done is by gravity on the body. So take note of these two statements. But in whichever case there, the same formula applies. That means for this case there, we can have that work done, W is equal to mass times gravity times height. Mass in this case is 100 times gravity in this case was not given. We can take 9.8 times height. Height in this case is about 2. So if I multiply all of these, 100 times 9.8 times 2, what do I have there? That's about 1960. Of course, that's work done. 1960, of course, is in joules. So I have 1960 joules. All right, so this is like a simple concept on how work is done. We'll take one final example on work done, right? Let me show you something. I'll take one final example on work done, and then we'll move over to energy. All right, so let's look at this question here. So this question here is this. In this question, you have to find. So in this question, we asked to find the work done from point A to point B. So let's call this W point A to B is equal to unknown. All right. And a second part, we are asked to state if in this case the work is done against gravity or the work is done by gravity on the object. So we are asked to answer that question for this diagram. So what do we do? First is first, we said work done, recall something. So first is first, recall that work done, W is equal to mass times gravity times height. So the question now be, what do I have here? I have my mass, all right, so the mass of P. This is an object, P. You say the mass of P is about 32 kilogram. So mass is given. Gravity is a constant, 9.8. So that's not a problem. The question now is this, what height will I use here? Because if I look at this, there are about two heights here. There's a height of 2 meters and there's also a height of 5 meters. So which of the heights do I use here? That becomes the question. Now, here's something to note. So in this case here, you can see very clearly that the height. Now, when we talk about the height, we're looking at the height at which the body moves. Now, the question is this: the body starts from where and ends where? The answer will be this: the body starts from point A and is being moved from point A to point B. The question now be from point A to point B, what is the height? So what is the height of AB? That's the question. That means in this question there, the work done from point A to point B will be equal to the mass of the body times gravity times the height from point A to point B. That's all. All right. Such that the work done, W, from point A to point B by the body is equal to the mass of the body, as we see, is 32 times gravity is 9.8 times what's the height from point A to point B? That's this distance from here to here. It's as easy as subtracting the total distance from here. So I'm saying HAB. Okay, let me write that one here. So I'm saying that HAB. Okay, fine. Here I'm saying that HAB is equal to total distance from here to here, which is 5, minus distance from here to here, which is 2. All right, 5 minus 2 gives you what there? 3 meters. That means HAB is equal to 3 meters. From here, if I multiply this becomes 32 times 9.8 times 3, and this gives about 940.8. Work done is measured in joules. So I have 940.8 joules. All right, so that's the concept about work. Let's look at the next concept there, which is energy. So if you enjoyed this class section, simply hit the like button and subscribe to this channel for more content. Also, I have prepared well over 100 classes on mathematics, physics, and chemistry with other science subjects too. All right. If you want to get access to my complete tutorial for JAM and WIRE candidates, simply visit my website www.jonaemmanuel.com/courses, and you see the JAM/WIRE classes. So you can simply go there and then make an order. It gives you a lifetime access to all the courses. All right, don't forget to like this video, leave a comment, tell us which video you'd want to see next. Thank you and see you in the next class.